Hey guys, welcome to part 2 of the Chapter 21 lecture on organic chemistry. We're still talking about different ways of representing structures of organic molecules. We learned how to go from Lewis structure to a condensed structure, and we had just finished talking about how to go from a Lewis structure to a skeletal structure, and I did a problem where we went from a condensed structure to a skeletal structure. So let's practice drawing these condensed structures and Lewis structures and skeletal structures on the following slide. Alrighty, so let's do the first line first. All right, so here we have a straight chain alkane. It's got 5 carbons. So we're just going to systematically list the carbons and the hydrogens. So the first carbon has 3 hydrogens. The second carbon has 2 hydrogens. The third has 2 hydrogens. The fourth has 2 hydrogens. And the fifth has 2 hydrogens. The fifth has 3 hydrogens. So you'll notice a pattern here with straight chain alkanes. The ends always have 3 hydrogens and all of the middle ones have 2. The skeletal structure of this is also going to be simple. It's just going to be a zigzag line. So again, I like to draw a little ball as my placeholder for my carbons. So I've got 1, 2, 3, 4, 5. So that would be pentane in skeletal structure. I think it is pretty sort of standard to make your line go up and then down, but it would not be wrong to draw the same molecule like this. 1, 2, 3, 4, 5. All right, that's 5 carbons. They're the same thing. One is drawn with the zigzag starting down, one's drawn with the zigzag starting up. It doesn't matter as long as you have 4 bond lines representing 5 carbons. And those hydrogens are all there. They're just invisible. They're assumed. All right, in the second one, we've got what we call a cycloalkane. It has 4 carbons, and so if it was straight, we would call it a pentane, but because it is cyclic, we call it we would call it butane, but since it's cyclic, we call it cyclobutane. And this one up here, I'll just go ahead and tell you, is pentane. All right, so let's draw the condensed structure for this. So it's going to be CH2, 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 like so. And in this one, I chose to draw the bond lines because I think it would look funnier without them, especially when it takes on a shape like that. For the skeletal structure, it's super easy. It's just a square. So cycloalkanes tend to just look like geometric shapes when we draw them in skeletal structure, and it's much, much easier. All right, now down to the third line, we have a condensed structure. We need to draw the Lewis and the skeletal structure. So the Lewis structure is, I'm going to draw all the carbons connected together first. So there's 4 carbons, and those last 2 carbons are connected by a double bond. And then I'm just going to fill in the hydrogens. 3 here, 2 here, 1 here, and 3 here. All right, for the skeletal structure, it's 4 carbons in a row, so it's 1, 2, 3, 4. And to draw that alkene double bond, I just draw a second bond line there, showing that carbons 3 and 4 are connected through 2 bonds. All right. The fourth one down, we've got 2 skeletal structures, and we're going to turn them in condensed and Lewis structure. So this fourth one here, we've got to count the carbons first. So we've got 1, 2, 3, 4, 5 in this first chain, in the straight chain. So I'll do it like this. 1, and I'll save room. I guess we should count the hydrogens too. So this first carbon, it's on the end, so it only has 1 bond line coming out. That means it has 3 hydrogens, and I'm just drawing the hydrogens as little yellow spots. All right, so that's a CH3. The next carbon has 2 hydrogens bonded to it because it already has 2 bond arms. So that's CH2. This carbon, the third carbon, has 3 bonds already, so it only has room for 1 hydrogen, so CH. This next carbon, the fourth one over, must have 2 hydrogens bonded to it because it has 2 bond arms. And then this last carbon has 3. So CH3. Now we're not done because there is that branch point coming down. So there's 2 carbons coming off of that middle carbon. So there's a C here and another C. And this one has 2 hydrogens, and this one on the end has 3 hydrogens. All right, so the condensed structure would look like that. Or another way to write it is, instead of having this bond here, to just write CH2, CH3, and just show that branch with a bond line there. All right, the Lewis structure, I'm just not even gonna bother because it's gonna take up the whole space that I have left. But I think you guys are pretty proficient at Lewis structures, and I won't make you draw too many of those because that's the whole point of learning condensed and skeletal structure. So let's say we don't need to draw the Lewis structures for these two. Let's just practice going between skeletal and condensed structure. So then for this last one, here's the carbons. So we've got 5 carbons total. This is a chlorine. It says Cl. So at the end of that line, there is no carbon because it tells us it's something else. It's a chlorine. So we have 5 carbons in a row. 1, 2, 3, 4, 5, and I'm leaving room to write their hydrogens. And coming off that third carbon, I'm going to go ahead and write the chlorine. Notice I wrote the chlorine sticking up, even though in the skeletal structure it's sticking down. It doesn't matter. It doesn't matter whether it's sticking up or down, as long as it's sticking off the right carbon. Now let's count the hydrogens. So this one has 1 bond, which means that there's 3 invisible hydrogens there. Any carbons that are at the end are always going to have 3 carbons, unless there's a double bond. Over here, 2 bonds coming out, so 2 hydrogens. Over here, 3 bonds coming out, so only 1 hydrogen. And then the last one, that fourth carbon, must have 2 hydrogens. So we basically just counted all of the hydrogens here. And we had to do that by imagining them because they're not shown in any form. We sort of do it through deduction and subtraction, basically, that we know all the carbons have 4 things bonded to them. So if they only have 1 bond, that means 3 hydrogens. If they have 2 bonds coming out, then there's 2 hydrogens. If there's 3 bonds coming out, then there's 1 hydrogen. And if there's no bonds coming out, if the carbon's bonded to 4 other carbons, then there are no hydrogens. So you'll practice some of those. All right, the other part of the chapter is the nomenclature part. Remember, nomenclature is a fancy word for naming things. And chemists have very specific rules for how things are named. And it's important because, you know, in a global scientific world, you have people all over the globe studying different compounds or doing different chemical reactions, and they have to have a way to communicate that all in the same language. So there needs to be chemistry naming rules so that everyone can speak the same chemistry language. So the system of naming organic compounds follows these rules, these IUPAC rules. I always forget what IUPAC stands for. It's like the International something something of Chemistry. International Physical Applied, I don't know, some association of chemistry. And these are the names of the alkanes, the first 10 straight chain alkanes that we talked about: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. All right. And But sometimes we have a single carbon group, a CH3, sticking off of a chain, or an ethyl carbon group, a 2-carbon group sticking off of a chain. So when it's a group that sticks off of a parent chain, of a main chain, all right, then we have that suffix -il. So methane is a straight chain alkane with just 1 carbon. But if you have a 1-carbon group sticking off of a parent chain, it's called a methyl group. So for example, with this branched chain molecule here, all right, what I've circled in red is what we call the parent chain. It's the longest straight chain of carbons. And it has 1, 2, 3, 4, 5 carbons. So we would call that parent chain a pentane. All right, but then there's 3 CH3 groups sticking off or branching off. And so these branch groups, we call those substituents. And so substituent is just the term that we use for these branched off points. And so a branch group or a substituent that contains 1 carbon is called a methyl group. As opposed to methane, it's a methyl group. If it had 2 carbons, it would be an ethyl group. 3 carbons, a propyl group, and so on and so forth. So that suffix basically just changes. So we're going to go through the systematic naming of branched chain alkanes in the next couple of slides. Straight chain alkanes are easy. They just already have a name. But when they have different branch groups coming off of them or substituents, then it gets a little bit more complicated. But if you follow the rules, you kind of always get to the right name and it starts to make sense. It can be intimidating because these names can come off as very long mouthfuls and look very complicated. But when we break it down, you'll realize it actually makes a lot of sense. Okay, so the first, we can break down naming, nomenclature, of organic molecules into 4 steps. All right, the first step is to find the parent chain. And what I mean by that is find the longest continuous chain of carbon atoms. So you might have to check a couple of different directions. So I could count it like this, 1, 2, 3, 4, 5, 6, and I get 6, that the longest chain is 6. Or I could do 1, 2, 3, 4, 5. No, that's not as long as 6. Or I could do 1, 2, 3, 4, 5, 6. That it was also a chain of 6. I could do 1, 2, 3, 4, 5, 6. All right, so there's a lot of different ways that I can count. A continuous chain is basically counting carbons that you can follow the carbon without lifting your finger up. Okay, so there's 3 different ways that I count this and I get 6. 6 is the longest chain I can possibly find. For ease, I'm going to go with that straight chain. So I'm going to say this is my parent chain, and I'm just going to put a box around it right now. So it has 6 carbons, 1, 2, 3, 4, 5, 6. So we're going to name the parent chain first. And a 6-carbon chain of a 6-carbon chain alkane is called a hexane. So the parent chain is a hexane. Great, so we've named this part of the molecule. Now, step 2 is to identify those substituents. Okay, so we've got 1 here, 1 here, and 1 here. This whole thing, this is one branch, this is one group. All right, so we've circled them, and now we want to name them. So the CH3s are each called methyl, if we look at that table on the previous slide. So we've got a methyl there, and a methyl there, and a 2-carbon alkyl group is called an ethyl. Okay, so they're made out of carbons and hydrogens, so they're called alkyl groups. We found our alkyl groups. And if there's more than one type, we want to list them in alphabetical order. So we have ethyl and methyl. So we want to list ethyl first and methyl second. Now it's going to say methylhexane. There's no space between there, but I did purposely leave a space between ethyl and methyl. All right. Another thing is this rule should probably be moved up here, actually, in step 4. So if there's more than one substituent of the same type, we need to indicate this by using the prefix di, tri, or tetra. Di means 2, tri means 3, tetra means 4. We do have 2 methyl groups. Sorry, I need to give myself more room here. So the fact that we have 2 methyl groups, we need to indicate by using that prefix di. Dimethyl means we have 2 methyl groups. All right, and then I'll rewrite my ethyl here. Okay, so now we have all of the substituents listed in alphabetical order, and we used a prefix di to indicate that there's 2 methyl groups. All right, now the only thing that's missing, the only thing we need to add is we need to add basically an address. If we think of the parent chain as sort of the street, each of the substituents has a different house number or street number. And so what we need to do is we need to label the carbons in the parent chain so we can give each of those substituents an address. Now, you can start labeling it left to right or right to left. And the rule is, for labeling, is you want to start at the end that's nearest to a substituent. So the substituents are really heavy on the right side. They're closest to the right end. So that's where we're going to start numbering. So this carbon, we're going to call carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. And now we can say the address for each of these groups. I'm going to need to erase this so I can have some more space to write. All right, so the ethyl is on carbon sticking off of carbon 4. So we say 4-ethyl, and those 2 methyl groups are both sticking off of carbon 2. So we say 2,2-dimethyl, and that's a comma, sorry. So let me just write this out a little bit neater. The full name here is going to be 4-ethyl-2,2-dimethylhexane. It's a mouthful and sounds really what's intimidating to a lot of students. But really, it's exact directions on how to draw this molecule. It tells us that we need to start with a hexane, and we need to add 2 methyls and 1 ethyl, and the 2 methyls each go on carbon 2, and the ethyl goes on carbon 4. So while it seems long and complicated, it actually makes a lot of sense. And so we just walk through these steps anytime we have a molecule and we can come to the correct name. A little grammatical comment that you might want to add to your notes here is that after, let's see, so notice that here we have a dash and here we have a comma. So if it's between a number and a letter, we use a dash. But if we have 2 numbers, like 2, 2, we use a comma. So that's just sort of a grammatical rule. Between a number and a letter, it's a dash. Between a number and a number, it's a comma. And that will come into play when you are doing the sapling homework. It won't accept the answer. It will remind you a lot of times, though, in the hints to make sure you use the right punctuation there. On a test, at this level, will not count you off if your punctuation is off, but it's good to start good habits early on. All right, so let's work through some other practice problems here. We have 3 molecules shown here in different, skeletal forms and condensed and sort of hybrids of the 2. All right, we're going to start with the parent chain. Now, if you have an alkane with a ring, a cycloalkane, the cyclic part counts as its own chain. So this is a 6-carbon chain. Okay? We don't count like 1, 2, 3, 4, 5, 6, 7, 8, 9. We count the cycle, the cyclic part, as its own chain. So the longest chain I see here is that cyclic part, the cycloalkane, which has 1, 2, 3, 4, 5, 6 carbons. So it is a hexane, but because it's cyclic, it's circular, it's not straight, it's a cyclohexane. Okay? So that's the parent chain. The parent chain is the cyclohexane, the 6-carbon ring. Now for the substituents. We've got, I'll put my little dots on my skeletal structure here so I can make sure I don't lose any carbons. So here we have a single carbon group, which is a methyl. If we look back at that table, and here, this branch is a 3-carbon group, and a 3-carbon group is called a propyl. So we're going to put those in alphabetical order. Methyl comes first, then propyl. So we'll put propyl here and methyl here. We only have one of each, so we don't need any prefixes like di or tri or tetra. The last thing we need, though, is we need to give them an address. So when we're numbering a ring, we want to start, there's no end, so you can't start at the end where the substituents are located closest to. You want to start at the biggest substituent. So in this case, the propyl is bigger than the methyl, so that's the carbon where we're going to start numbering it. And now we want to continue numbering toward the direction of the next constituent. So essentially, we want our substituents to all have the smallest number possible in the address, if you will. So we see that the propyl is sticking off of carbon 1. So I have dashes that separate my numbers and letters. And the methyl group is coming off of carbon 3. So we call this 3-methyl 1-propyl cyclohexane. It's a mouthful, but again, it still follows this same series of steps. Let's do it again. You can't practice this enough. All right, so I'm going to look for the parent chain, the longest straight chain. 1, 2, 3, 4, no. 1, 2, 3, 4, 5, 6. Cool. 1, 2, 3, 4, 5. Okay, 6 looks like the longest chain. So this in purple here, I've got a chlorine sticking off. That's not a carbon. I'm not counting that. The carbons I'm counting in my parent chain are these 1, 2, 3, 4, 5, 6. So again, we have a hexane, not a lot of variety here. It's a straight hexane, so I don't need that cyclo prefix, hexane. That's the parent chain, cool. Now I'm going to go ahead and circle the substituent groups that I need to name. So I've got a methyl group, and over here, a chlorine. We call that, if you have a halogen sticking off, we just say chloro. If it was a bromine, we'd say bromo. Iodine, iodo. All right, and then those are the only non-carbon containing groups that we're going to learn how to name. All right, but each of these is a methyl group. All right, chloro comes first in the alphabet before methyl. So chloro and then methyl. All right, technically methyl, hexane should all be one word. So I'll draw it closer together. And now we just need to give addresses. So we want to start on the side that's closest to, that has a, substituent. So if we start on the left, if we started here, 1, 2, 3, we wouldn't hit a substituent until carbon 3. But if we start on the other side, the left side, I think I got my left and right mixed up. All right, there's a chlorine right there on carbon 1. So our first substituent would be on carbon 1. So we want to start labeling it on that side so we can have a substituent with the lowest possible number address. So I've numbered my carbons, so now I can give them all an address. So the chlorine is on carbon 1. And oops, I forgot one thing here. There's 2 methyl groups, so I need to use that prefix dimethyl to indicate that there's 2 of them. Another clue that there's 2 of them is that we're going to have 2 addresses. So there's one on carbon 3, and the other one is on carbon 4. So I do 3, 4. So this molecule is called 1-chloro-3,4-dimethylhexane. It's a mouthful, but they are exact directions on how to draw this molecule. And then let's do one more. So I'm going to look for the longest chain here. 1, 2, 3, 4, 5, 6, 7. Or we could do 1, 2, 3, 4, 5, 6, 7. Oh, I just found a longer one. 1, 2, 3, 4, 5, 6, 7, 8. That is the longest chain that I can find, 8. So this is an octane, is our parent chain, except we have this double bond here. And if we have a double bond in our carbon chain, we don't have an alkane, we have an alkene. So this is not octane, it's octene. All right, so just like if that alkane was in a cyclic form, we had to make it cyclohexane. All right, if there's a double bond present, we change that suffix to -ene instead of -ane. All righty, so I'm just gonna like, how about this? I'll just draw a line through my parent chain. That way I know I've already named that part of the molecule. That was the octene. Now I'm gonna circle the substituents. All right. This carbon group here, this carbon group here. These hydrogens, they are not substituents. They just happen to be showing that hydrogen sticking off of the carbon. But a hydrogen by itself is not a substituent. It's included with that carbon in the chain. So the only 2 substituents are this methyl group right here and this ethyl group right here. All right. Technically, though, we have an octene. That means there's a double bond in here somewhere, but we need to be able to say where that double bond is, between which of those 8 carbons it is. So this this double bond is also going to need an address. So I'm going to circle it as if it's a substituent because we need to figure out how we're going to start numbering this chain. And I just caught myself up because if we start numbering it on the left side, 1, 2, we hit a substituent, that methyl group, at carbon 2. If we start labeling it on the other side, 1, 2, we hit a substituent of the double bond at carbon 2. So there is a sort of ranking system. There are certain substituents that have priority when you have a tie like this. The question is, which one has priority, the methyl group or that double bond? And I'm not 100% sure, but I'm going to go with the double bond because I think that is the one that has priority. So I won't give you any of these on the test where you have to decide which has priority because, again, introductory, we're not going to learn priority groups here. So, but we'll say for the sake of this problem that the double bond has priority, so we're going to start labeling it this way. 4, 5, 6, 7, 8 are our 8 molecules. So I'm going to list these in alphabetical order. We've got ethyl and then methyl. All right, that double bond is on carbon 2, so 2-octene. The 2 is referring to the ene, the alkene group. The methyl is on carbon 7, And the ethyl is on carbon 4. So we have 4 ethyl, 7 methyl, 2 octene. All right, just enough examples for now. Practice some of these on your own. Practice makes progress. And when we come back, we will continue.